Welcome to all of you in Quantum Mechanics lecture series. Myself, Professor Dr. Arvind Sharma, HOD, Department of Physics, Government, Lohia College. Today's lecture topic is related to applications of WKB approximation method. First topic, we are going to understand about the connection formulas for penetration of a ring. Connection formulas for penetration of a ring. Okay, so this problem is like that. A problem is mixed where potential function is slowly varying and not slowly varying. If we try to understand the problem, which kind of problem we want to consider here, to understand such kind of problem, we must understand this geometrical or diagrammatically representation. This shows potential versus distance cap. Okay, how potential changes with position. Here, energy is have this constant value, but potential changes like this curve. This is the curve that changes that gives the how potential varies with the position. Here is a point x equal to a. The position x equal to a where potential and energies are equal. Okay. This is the part where E and V are equal and this position is taken or considered x equal to E. In the left side, energy E is greater than V. This is the second region. This is the second region. And on the right side, the region of V greater than E, potential V is greater than E, and it is called first region. So, before starting this article, you must understand this diagrammatical or geometrical picturization or configuration. Clear? Okay. Now, we know that WKB method is only applicable where potential function does not change too rapidly or potential function is slowly varying function of position. Okay, does not change too rapidly, because in the regions approximation method is not do not apply. In such kind of regions where potential function is changes rapidly. So if there are two regions very near to some region where in some part of the region potential function is slowly varying and other part it is not varied slowly. Okay, so where potential varies slowly, WKB method holds or applicable. But where function varies rapidly, then WKB method is inapplicable. Okay, there are two kinds of solutions, or there are two kinds of regions. In one region, WKB method is applied or applicable where potential function is slowly varying, and second is where potential is rapidly varying or varies rapidly, where WKB method is inapplicable. Now, we find the solution in the regions of inapplicability of WKB method, some by some other methods. What is our aim? We are trying to such kind of regions or solutions in such kind of regions where WKB method is incapability, or that means WKB method is incapable or not possible by WKB method to solve the problem. Okay. Now carry it to the regions where WKB method is applicable. What is the solution or what is the method? Some other words, carry it to regions where WKB method is applicable. How it is possible? In one region, WKB method is applicable. In other region, WKB method is not applicable. And we are trying to carry it to the regions, okay, by some other methods. By some other methods and carry it to regions where WKB method is applicable. So to do this, in order to connect these two solutions, we need connection formula. There are two solutions and we are trying to connect these solutions. One is WKB method solution, second one is by another exact method. We have some solution and there must be some connection between these two solutions. In order to connect these two solutions, we need for the connection formula. Okay, to treat the problem of barrier penetration. This problem is barrier penetration. You all are familiar with this problem because you go through this problem in your UG classes and in semester first. Okay, where WKB method is right. Okay, but there are two regions. One region is E greater than B, that is second region left to the x equal to A, and V greater than E, first region to the right side. And what are our aim? Connect solution in the regions V greater than E with those where E greater than E. Okay, connect these solutions. Our aim is to connect these two solutions, region where B greater than E and with those where E greater than. Okay. Consider the potential barrier shown in this figure. Suppose energy of the particle is such that E बराबर V at x बराबर A, x बराबर A equal. Classically, the particle should show down to zero velocity at this point. Classically, because x equal to A and equal to V. So classically, the particle velocity becomes zero at this point. That means it turns back. But quantum mechanical, we know that the wave penetrates some distance further into the barrier if E equal to V or E less than V. Okay. So in that case, wave penetrates some distance between some distance into the barrier. Obviously, we cannot use WKB approximation in the region near x equal to a. Near x equal to a, we cannot use WKB approximation because E equal to V. We cannot use WKB method near here, regions near x equal to a, because E equal to a and condition for applicability is breakdown. Okay. Thus, if we start with a given solution at some distance to the right, we are taking some distance, we are taking some distance to the right of x equal to a in the first region. Okay. And now, what is the solution at some distance to the right of x equal to a? That is in the first region. The form of the solution wave function is given by psi equal to 1 upon under root p1 exponential integral a to x p1 dx upon h naught. Okay, this is the form of wave function to the right side of x equal to a, where p1 equal to under root 2mv minus. From WKB method, we know that sufficient distance to the left region in region 2, we are taking sufficient distance to the left. The approximate solution is given by the superposition of these two terms. We know this is the region on the right side. This is the region, first region on the right side, where V greater than E. But in the region, second region, left to the x equal to a, the solution is given by superposition of two terms, exponentially plus iota and minus iota. Psi equal to a upon under root p2 exponential plus iota integral a to x p2 dx upon h cut plus b upon under root p2 exponential minus iota integral a to x p2 dx upon h cut, where p2 equal to under root twice m e minus v. So you all know about such kind of solutions, because we are taking in such kind of solutions you are familiar, because you go through such kind of solutions in UG and MSc first semester. Okay. Here A and B are unknown constants. Here A and B are unknown constants. And the values of A and B cannot be found by the WKB method alone. Only WKB method is not sufficient to calculate the values of unknown constants A and B, because they are determined by the solution in the region of incapability of WKB method, where WKB method is incapable. So to obtain the values of A and B, if we want to calculate the values of A and B, we need an exact solution near x equal to A, because near x equal to A, WKB method is incapable. Okay, but it is too complex problem to be solved. Problem becomes complex. Problem becomes complex if the WKB method is applicable at some distance from x equal to a and incapable at small enough region near x equal to a. Near the region x equal to a, WKB method is incapable, but at some distance from x equal to a, WKB method is capable or applicable. Okay, then the potential function can be. In such kind of situations, potential function can be represented approximately by a straight line within the region with slope equal to the potential curve at classical turning point x equal to a. This is the very important point to be noted, that potential function can be represented approximately by a straight line within the region. Which region? With slope equal to the, in this region, slope equal to that of potential curve at classical turning point x equal to a, as E barabar V, x equal to a and V minus E equal to C x minus a. Okay, so in such situations V minus E equal to C x minus a, and C is a constant and it is equal to delta V upon delta x at x equal to a. Hence, in the region x equal to a, Schrodinger equation reduces to the approximately one-dimensional Schrodinger equation reduces to the del 2 psi upon del x2 minus twice m upon h square cx minus a psi. Now, this is a difficult equation. This is a difficult equation and solved by Bessel function of order 1 by 3. This is a difficult equation and it can be solved by the using Bessel functions of order 1 by 3. Now solution of this equation 3 is carried far enough from x barabar a. What we are trying? We are trying to solve this equation far enough from x equal to a. So WKB method is applicable because near x equal to a, WKB method is not applicable. So we are taking the position far enough from x equal to a where WKB is applicable. In this way we will determine the constant C and P. Okay. Here we shall simply write the results without going through the complex procedure. Here we shall simply write the results. We are not going towards the complex procedure. Okay. So some terms you must remember. Okay. First case, barrier to the right. Barrier to the right, the region is B greater than E, right of the x equal to A, where P1 given by this expression, P2 given by this expression. Now let us consider far to the right of x equal to A, WKB approximation, which is exponentially, okay, and given by this function psi equal to b upon under root p1 exponential minus integral a to x p1 dx upon h. Similarly, For left side, the connection formula states that this solution approaches. Connection formula states that this solution approaches psi 2 equal to this term. 2b under root p2 cos integral a to x p2 dx h cat minus pi by 4. You should remember. You must remember. You must remember this function because we are not going to briefly to solve the solution. We are taking only these functions down. Now connection formula may be expressed. Both functions should be equal. This function and this function. Okay, this is the first function and this is the second function. Both are equal. So b from both sides cancelled and remaining terms are 1 upon under root p exponential minus integral a to x p1 dx upon h cat equal approximately. This is approximately to this term. This is equal to this term. Okay. Similarly, if the approximate solution is an increasing exponential to the right side. If approximate solution is a increasing exponential, that means exponential is increasing to the right side, then connection formula shown by the relation, this term taken here, this is cosine, okay, and here this becomes sine, and there is a minus symbol here. This is also here minus symbol. Okay, so you can easily see that right side cosine, here is this is sine. Okay, and right side is same expression. Here minus sign is here and it is taken outside from the integral. Remaining term is same. Okay, so these expressions must be remembered by. Barrier to the left. Now second case where solution which decays exponentially to the left of the x equal to a, and connection holds here. This is the first relation, and if solution increases exponentially, in that case this becomes sine, here becomes cosine becomes sine, and the relation you can easily see that such kind of relation is again comes. So these expressions must be remembered by you directly because that these solutions are not solved. Okay, these are taken directly to explain the things. What is our aim? Our aim to understand the how to solve the problem. We are not going mathematically. Okay, so these expressions are taken directly, and you must remember these solutions. Now it may be noted that connection formulae enable us to only obtain the relations between the solutions. Which kind of solutions and between which regions? Region at some distance to the right of the turning point x equal to a, with those in the region some distance to the left. X equal to a is the turning point, Okay, x equal to a is the turning point, some distance to the right and some distance to the left of x equal to some distance to the right or some distance to and some distance to the left. Now, in order to form the wave function, this is the very important point to be noted that in order to obtain the form of the wave function in the intermediate region, we should consider exact solution, and this involves Bessel function of order of 1 by 3. Okay. Now, for applying WKB method, the following requirements should be satisfied. These are the conditions necessary if we want to apply WKB approximation. In such kind of problems on either side of the turning point, there exist regions where potential function changes slowly. There is no problem, there is a turning point, but the regions, there exist regions when potential function must be changed slowly. In such kind of problem, WKB method is applicable on the either side. Though on the both sides, such kind of regions must be present where potential function is slowly varied. Okay. In regions near the turning point x equal to a, where it is not applicable, that is WKB method is inapplicable, then kinetic energy must be represented by a approximately straight line E minus V equal to C x minus A. In other words, potential should not undergo a large fractional change in slope within this region. This point is very important to understand. Potential should not undergo a large fractional change in slope within this region. Okay. So we are taking the straight line, hence potential changes, but frictional change is not too large. Okay. So potential should not undergo a large frictional change in slope within this region. So these are the two conditions for the application of WKB method. Inside the barrier, WKB approximation begins to hold after inside the barrier becomes appreciably greater than unity. If this is the expression, inside the barrier, WKB approximation begins to hold after integral a to x integral to under root 2mv minus x dx upon h cut becomes appreciably greater than unity. So these are the conditions which are necessary for the application of WKB. In the next topic or next lecture, we applied the WKB method to calculate the probability of penetration of a barrier. Okay, thanks to all of you.